Okay, we are on 821 day 2. So this is the last true lesson of the week. Tomorrow you will have Khan Academy practice, and we are going to continue to look at the difference between real numbers and imaginary numbers through roots, which are x-intercepts. So let's just start right off with 67, and it says when a graph crosses the x-axis, oftentimes we say that x-intercepts are real roots of the equation that results when y is 0. You have seen that solutions to equations, however, can be real or complex. Okay, so complex numbers implies imaginary, taking the square root of a negative. So it follows that roots can also be real or complex. Compare and contrast what happens with the graphs of equations for 3 cases in part A through C below. So what we're first going to do is look at, in graphing form, a parabola, and it's has no stretch factor, but we see that the vertex is going to be at what? -3, -4. So we can go ahead 1, 2, 3, 4. Put a point there. Sorry, I'm going to have to enlarge this screen. Okay, there we go. Let me erase. Let's try this again. I'll make my pen a little thicker. 2, 3. Okay, so we have our vertex there. Then we can go out 1, up 1. And then we can go out 2, up 1, 2, 3, 4. And we can make our parabola. Okay, so it's asking what are the roots? Well, we can kind of see in our picture what they are, but if we want to go ahead and do this systematically, we can say 0 because roots means x-intercepts, y is 0, and we have x plus 3 squared minus 4. So how do we solve graphing form? We solve by undoing. So we're going to add 4 to both sides, and we have x plus 3 quantity squared. Then we are going to take the square root of both sides, and we know when we take a square root of a number, we have to consider the plus or minus case, so we get plus or minus 2 equals x plus 3. Okay, so at this point, we can subtract the 3 over and see that x equals, think about it, -3 plus or minus 2. So really, what is that going to give us? -3 plus 2 is -1. -3 minus 2 is -5. If you look on your graph, we can see that those are indeed the real roots of this first graph. Okay, so we see that this first example, the function has real roots. Okay, but now we move into the second example, that is quantity x plus 3 squared. So again, it is a parabola because we are squaring the quantity, and we want to think of the vertex, which in this case, what is the vertex going to be? The opposite of positive 3. Whoa, my pen is too thick. The opposite of positive 3, which is -3, and then we have nothing tacked on at the end, so it's 0. So -3, 0 is our vertex, and then again, we have no a value, it is 1, so we have no stretch or compress, so we can do the normal shape of our parabola. And we can quickly see that how many roots are there going to be? There is just going to be 1 root, but if we want to solve this systematically, we can do 0 equals x plus 3 quantity squared, square root both sides, and when I square root 0, yeah, you can put the plus or minus, but adding 0 and subtracting 0 is just plain old 0, so that's the only number that we ignore the plus or minus, and then we subtract 3, so we get 1 root of x equaling -3. So we would say that there is 1 real root. Okay, and that makes sense because if we think about our polynomials from last section, okay, it is bouncing off of the x-axis. So we know that the factor has to have an even power, which look, there is an even power. So it's all kind of flowing together. Okay, the final task says to sketch the graph of quantity x plus 3 squared plus 4. So can we find the real or the roots by looking at the graph? Okay, well, let's go ahead and graph. The vertex is -3, negative or +4. So we have 1, 2, 3, 1, 2, 3, 4. And then it's opening up like a cup. There is no stretch factor, so out 1, up 1. So here is our parabola. So right away, can we find the roots? Can we find those x-intercepts? Those two words are synonyms. And the answer is no, we can't. Because it does not cross the x-axis. So in this case, when we don't see our function cross the x-axis, that means that the roots are going to be complex. Complex, when you see that word, that is going to immediately target imaginary. Okay, so let's go ahead and pretend that we're solving, or we are. We don't need to pretend. We have 0 equals quantity x plus 3 squared plus 4. We subtract our 4 over, and then we get ready to take the square root. And when we square root both sides, we see that we are rooting a negative. So we get that the root of -4. What should we put out front? Plus or minus. So plus or minus the square root of -4 is equivalent to x plus 3. Now I need to subtract my 3, so look at how I write my answer. We have -3 plus or minus the square root of -4. Okay, now is where we want to get this into imaginary form. So we said we can rewrite it as -3 plus or minus the square root of 4 times -1. And this is a good review from yesterday. What is -1? It is equivalent to I squared. So we have plus or minus the square root of 4i squared. And then what is the square root of 4? It is 2. And then what is the square root of I squared? It's I. So these are the complex roots of the original function. How did we know they were going to be complex? Because the graph did not cross the x-axis. So you will only have complex roots when the graph is not touching that x-axis, but yet you're solving for when y is 0. So let's make a general statement about the relationship make a general statement about the relationship between the graphs of parabolas and the kind of roots that their equations have. Okay, I'm going to back up for a second. Sorry, I just had a thought. And even though I wrote the complex answer like this, yesterday we talked about imaginary numbers, let me check real quick in my notes how I want you to write this. No, we want you to write it like this. We want the real component first, and then we want the imaginary component second. Okay, so that's good. Now, if you wrote it as plus or minus 2i plus or minus 3, that minus should be there, then that's fine as well. But please make sure that that minus is indeed there. Okay, so let's go ahead and make our general statement, and I'm going to type this in. It'll be more legible. So here we go. If the graph crosses the x-axis, the equation has real roots. Okay, that's very important. Now, on the other hand, let's change color. Oh, it changes the whole thing. Darn. Okay, if the graph crosses or does not the x-axis, the equation has complex roots. Okay. If the graph only touches the x-axis, there is only one root. If it graph only touches okay, and again, this is all for parabolas, so let me be clear there. This all, whoops, we want my pen. This is all for quadratics, for parabolas. The key thing is to know if we're crossing the x-axis, we have real roots. If we are not crossing the x-axis, we have complex roots. Very, very, very important. Okay. So now what we're going to do is jump into this idea still of finding problems that we used to think we couldn't solve, but now that we do have imaginary numbers, we can assign a solution. So on this set of axes, what we're going to do is we are going to sketch the graphs x squared. So let's go ahead and do that first. So I have my vertex, and then I have out one, up one, and then up 4. So here is my parent function, y equals x squared. And then we have a linear function, which I'll do in red, of starting on -5, and then going up 2 over 1, up 2 over 1. And we can draw, let's see if I remember my line tool. Draw my line through there. Okay. So, we want to go ahead and solve the system of equations. But what does the solution to a system of equation give? It gives the intersection point. Well, what do you notice about these two functions? Dot, dot, dot. They do not intersect. So, normally, we would have gotten no solution. But now I'm guessing that the solution is going to be what? It's going to be complex. It's going to be imaginary. So let's go ahead and solve algebraically. We already know that they don't cross, okay? But let's see what that's going to look like if we do it by hand. So I want to use equal values because they're both solved for y. So if I'm going to solve, I'm going to think about x squared equals 2x minus 5. And when I take a step back, I see that that is what? Quadratic. So I want to get everything to one side and keep my x squared term positive. So I have minus 2x plus 5 equals 0. Now, if I think about numbers that multiply to be 5, which is just 5 and 1, that's not going to get me anywhere near -2 when I try to add them together. So I am going to have to do the quadratic formula in order to solve this. Okay, so this is going to be quick because we shouldn't have that mastered. So we have x equals the opposite of b plus or minus the square root of -2 squared minus 4 times 1 times 5 all over 2 times 1. So I'm just going to keep it as 2. From here I have x equals 2 plus or minus the square root of 4 minus 20 is -16 all over 2. So right at this point you would have stopped and said no real solution. So maybe we can write that in, no real solution. So we need to think about the imaginary solution. Okay, so for the imaginary solution, we are going to go ahead and rewrite root of -16 as an imaginary number. Now I'm going to review the other way I taught you yesterday to deal with those negatives under the square root. Is you're simply going to remove the negative and put an I because the square root of 1 is I. If you keep in mind, we can rewrite the square root of -16 as the square root of 16 times the square root of -1. Well, what's the square root of 16? 4. What's the square root of -1? We memorized that yesterday. That is I. That is something to memorize. So I know that the square root of -16 is 4i divided by 2. So then from there, everything is divisible by 2, so I get 1 plus or minus 2i is my solution. Okay, but that is just what x equals. So now, in all systems, we have to figure out y. Well, the good news is we can take advantage of the linear equation to figure out y. So I'm going to plug in each one of these separately into my linear function and solve for y. So I'm going to do y equals, let's see, I have 2 times 1 plus 2i minus 5. I'm just replacing my x with 1 plus 2i. I've been keeping it in parentheses. And then I'm going to do the math. So y equals 2 plus 4i minus 5. So y equals, let's see, 2 minus 5 is negative 3 plus 4i. So my first solution is 1 plus 2i, comma, y is 3 plus 4i. You've got to pair the correct x and y values together. So that's my first solution. Okay, now for my second solution, I need to go ahead and do that again, but I'm going to do 1 minus 2i. So I have y equals 2 times 1 minus 2i, and then minus 5. So I have 2 minus 4i minus 5, and I have negative 3 minus 4i. So my other solution is 1 minus 2i, comma, negative 3 minus 4i. That is the y value that goes with that particular x value. So we can't see these on the graph. These are imaginary solutions. So it says on part C it says, discuss your results with your team. What could these solutions mean? Well, these solutions are imaginary. The solution is imaginary. If things don't cross, if things don't touch each other, then you know the solution is not seen on a graph, and that's why we use the word imaginary. Anything with I involved is not going to be present on the graph. Okay, so we're going to end with one more question, and it's similar, but just not using a quadratic. It's using a rational function. So it says, do the graphs of y equals 1 over x and y equals negative x plus 1 intersect? What kind of algebraic solutions will they have? Verify your answer. So let's go ahead and use our knowledge of parent functions and graph y equals 1 over x. Okay, that is the hyperbola, where we are in quadrants 1 and 2, but there is an asymptote at the y-axis, so we do not cross the y-axis. And then if I go ahead and graph negative x plus 1, I'm going to start at 1, and I'm going to go down 1 over 1. So my line, my linear function, is going to be like so. Okay, so what kind of solutions will this system have? Well, we see that the graphs do not cross, so the system is going to have imaginary solutions. Okay, again, we're looking at the system. Where do the graphs intersect? So that is our prediction, is that we are going to have imaginary solutions. So once again, we're going to use equal values method. So I put 1x equal to negative x plus 1. And then I can go ahead and multiply up by x. So I get 1 equals, I have to distribute, so I'll show that, x times negative x plus 1. So I have 1 equals negative x squared plus x. So if I move everything to the left-hand side to get my x squared negative, I have this, x squared minus x plus 1. And then I don't think that I can factor this, and we're anticipating imaginary solutions, so we go ahead and use the quadratic formula. So because we're set equal to 0 as well, x equals the opposite of 1, negative 1 is 1, plus or minus the square root of b squared. So negative 1 squared is 1, minus 4 times 1 is negative 4, over 2 times a is 1. So I'm just kind of shortening the quadratic formula because it's old news. So we have 1 plus or minus the square root of negative 3 over 2. So right here is when we know that we have imaginary solutions, because we can't square root a negative number to get a real solution. So be careful how you answer that question from now on. So I have x equals 1 plus or minus 3i. Okay, we could go through the whole process, that break it up into root 3, root negative 1. The root of negative 1 is I. So I have 1 plus or minus 3i over 2. That is the x values of the intersection point. Okay, so what would we do? We could plug back in and solve for y, but at this point we have confirmed that the solution will be imaginary. So based on this right here, we have confirmed the solution is imaginary. Okay, because there is an I. There is a component of the square root of negative 1. Okay, so starting to look at systems of equations with imaginary numbers. So it's just all going to come full circle. Great job. Keep it up. We are seeing a light at the end of the tunnel. Let me know if you have questions, and great job with 8.2.1.